Hello, grade 12. Welcome to the grade 12 mathematics summer lessons. And today we'll be focusing on part 3, which is exponential and logarithmic functions. Okay, grade 12. Let's take a look at the content outline. If you can check the content outline on topic 2, we focus on functions and inverse functions, right? So functions was our part 1 and our part 2 was inverse function. So this is part 3 of our session, and today we're going to be focusing on topic number 3, which is exponential and logarithmic functions, where we'll just do some quick revision on exponential functions, and we'll also focus on the logarithmics rules and logarithmic functions. So don't forget, we are still using these two textbooks where we are extracting our notes and some of our examples from them. So it's Platinum Mathematics Learner's Book and also Mind Action Series Mathematics Textbook and Workbook. Okay, let's just do some quick revision on exponential function. Very much aware that in grade 10 and in grade 11 you did exponential function, right? So an exponential function, you know that its general formula can be represented by y is equals to a times b exponent x plus p plus q, where we know that our b must be greater than 1, right? So that's just the general formula or the standard formula for an exponential function, right? So let's also take a look at some shape and properties of an exponential function. As you can see in the pictures below, we have an exponential function y equals to b exponent x, and here the restricting is that b must be greater than 1, right? For example, b can be equals to 2, b can be equals to 3, 4, like that, right? And on this other side, we have y equals to b exponent x, but your b must be between 0 and 1. And in most cases here, it's where you find that your b is actually a fraction. For example, you can find 1 over 2 exponent x like that, 1 over 3 exponent x like that. So we know that our b here is between 0 and 1, right? So that's the shape of the graph. But how do you really identify the shape looking at b, right? So if you check the first graph where your b must be greater than 1, it's mostly where you find your b is equals to 2, b equals to 3, like that, where you have your exponential function as 2 exponent x, 3 exponent x, 4 exponent x, like that, right? So we call this function an increasing function, and this is its shape. And most of the cases, I just tell my learners that this is an increasing function, right? We say this is an increasing exponential function. As you can see, it's an increasing exponential function. And why do we say it's an increasing exponential function? Because as the value of x are increasing, also the values of y are increasing. Or as the value of x are decreasing, also the value of y are also what? Are also decreasing. Okay, let's take a look at what I'm trying to say here. So if you check when this graph is moving like that, you can notice that the value of x now are increasing. They are moving from negative to positive. They are increasing, right? Also, the values of y, it's from 0 there, and it's also going up. As the values of x are increasing, also the values of y of the graph are also what? Are also increasing. So, but if we can choose maybe to go this direction, as we are moving down, the values of y are decreasing, as you can see. Also, as we are moving down, as we are moving towards that side, the values of x are also decreasing. So they're doing the same. So we call this function an increasing function. But how do you know? You check the value of b, and also that shape can help you. So if b is greater than 1, for example, it can be 2 exponent x, 3 exponent x, 4 exponent x. That is an increasing exponential function. Why? It is because the values of x, as the values of x are increasing, also the values of y are increasing, or because as the values of x are decreasing, also the values of y are decreasing. So that function is called an increasing exponential function. Okay, so one other way to memorize this, you can just raise up your two hand, or let me just draw you a picture, maybe of a maybe like this, so that you can see. Yes, yeah, just that picture. So you can see that this is the left this is the left hand, right? But on my side it's just the right hand. I don't know if that will make sense. So on my side is just on the right hand side. If I raise my right hand side, it's gonna show me something like that. It's just that here on the picture you'll think maybe it's on the left hand side, but because it's reflected like that. But on my side, if you raise your right hand, you'll have something like this shape, and you know that right hand indicates something like that are positive or something that are increasing, you see. So you can just basically memorize it in that way to say, okay, if I raise my right hand, that shape will be of an increasing function. When I raise my left hand, that shape will be of a decreasing function. But otherwise, you can also look at the values of b and check. Let's move to this one of a decreasing function. We say your b must be between 0 and 1, and I told you most cases you'll find that your b is a fraction, maybe 1 over 2 exponent x. So that 1 over 2 is between 0 and 1, right? So we call that function a decreasing exponential function. It's a decreasing exponential function. Why is it decreasing? Because the values of x and y are doing opposite things, right? Not like here in our first exponential function where we found when x is increasing, y is increasing. When x is decreasing, y was also decreasing. Then we say this is an increasing function. But in this case now, you find that the values of x and y are doing opposite things. As x is increasing, you'll find y being decreasing. Or as y is decreasing, you'll find s increasing. Okay, look at what I'm saying. If you check, if we move backward like this, you'll notice that the values of x are what? Are decreasing. But look at the values of y. They are going up there. They are what? They are increasing. So we then conclude this is a decreasing function because the values of x and y are doing two opposite things. So it makes that function to be called a decreasing exponential function. But however, you can just use your value of b just to memorize, to say if my b is between 0 and 1, then it's a decreasing function. Okay, so if you check, both graphs passes through point 0 and 1, right? Both graphs, they have like a y-intercept of what? Of 0 and 1. Let's come to the domain. What do we mean by domain, right? So I don't want you to just memorize that always in an exponential function the domain is x, is the element of all real numbers, although some teachers may just encourage that kind of scale to say, okay, if you check all exponential function, the domain will just be x is the element of all real numbers. But it's quite dangerous sometimes, right? So what is the domain? What do we mean when we say domain? When we say the domain, we are obviously focusing on the values of x, right? But now in this case, we are saying, if we want the domain of this graph, we are saying, what are the values of x that your graph will cover, right? Or that your graph is taking up or will take up. So you are actually focusing on the values of x in which your graph will take, right? So when they are saying x is the element of all real numbers, they mean that this graph is going to take all the positive and all the negative values of x, hence element of all real numbers. So real numbers include the positives and all those negative values, right? So that's why they're saying x is the element of all real numbers, because this portion of the graph is going to infinity, is going to cover all the positive values, all the negative values of x. This portion, this side, is going to be covering all the negative values of x. Same as in this graph. This portion is going to cover all the negative values of x. This portion, all the positive values of x. Then the domain, we just say x is the element of all real numbers, right? X is the element of all real numbers. Let's come to the range. The range, what do we mean by range? By range we mean what are the values of y in which our graph will cover, right? Or what are the values of y that makes up our graph, or that our graph will pass through, right? Okay, so if you can check in this graph, right, you must know that in an exponential function there's always an asymptote, and an asymptote is a line and just an imaginary line that your graph can never touch, or that it can never exceed. Immediately if it touches that line, your graph becomes undefined. So in this case you can see that our graph, as it is moving down through the y-axis, if you check the y-axis, as it is moving down, it starts to bend towards the x-axis, but it will never exceed that x-axis, right? Because that is its asymptote. So its asymptote is when y is equals to 0, right? That is your value of q on the graph. So because the equation is just y equals to b exponent x, then we can see that we know that plus q, so our q is 0. So that's the asymptote. Also in this side, the asymptote is 0. The graph will never exceed that point, right? So that's the asymptote. Okay, so you can get the range if you know the asymptote, to just say y is greater than that asymptote, or y is less than that asymptote. It depends whether your graph is on the positive y-axis or on the negative y-axis. But our graph here, it's on the positive y-axis. Look at this. So we can see that from here up to there, those are the values of y that our graph will cover. So that is why our range will just be y will be greater than 0. We cannot say equal to 0. Why? Because the graph can never touch the asymptote. So 0 is the asymptote, it can never touch. So that's why we're saying from 0 and above, but 0 being excluded, that is the range in which our graph will be covering in terms of the values of y. Okay, we also talked about increasing and decreasing function. That's okay. And also the asymptote y equals to 0, and also the horizontal asymptote like that. So you can see that the two functions are the reflection of each other about the y-axis. You can see that these two functions are basically the reflection of each other about the y-axis, right? So if you reflect this graph about the y-axis, definitely gonna get this other graph. Okay, let's take a look at unit 2, which is this new kind of function that you are introduced to in your grade 12, known as the logarithmic functions. Logarithmic functions, right? So the logarithmic functions. What is the logarithmic functions? That's the first question that you must ask yourself. Okay, so now what happens is, if we reflect our exponential function about the line y equals to x, right? If you reflect any exponential function about the line y equals to x, so the new graph that will form will be called the inverse of that exponential function, right? But that new graph is now called a logarithmic function. Okay, so it's basically called a logarithmic function. So what actually happens is that they reflect an exponential graph about the line y equals to x, and the new appearing graph is now called what? The logarithmic functions. Okay, so let's just basically take a look at really closely at this logarithmic function. So for example, its standard form is y is equals to log ax, right? So this is the standard form for our logarithmic function. Sometimes they might say plus q if they just want to do that, but let's just use this this one. It's much easier to know. So y is equal to log ax. So log, you can see, because this is a logarithmic function. So if you see this equation, just know that, okay, it was determined by actually reflecting an exponential function about the line y equals to x. So and y will be equals to log base a x if only x is equals to a exponent y. So that's the condition, right? So y is equals to log base ax x if only your x is equals to a exponent y. So this x here must be equals to a exponent what? Exponent y. That's the condition where your x must be greater than 0. It means this x here cannot be equal to 0, because immediately when it's equal to 0, then it becomes undefined, right? And also your a must be greater than 0, but your a must not be equal to 1, right? So your a must be greater than 0, but your a must not be equal to 1. So that's basically its condition. So but I really want you to take a look closely at this rule, first rule of log, and it's coming from its standard formula. It says log base a x is equal to y if only x is equal to a exponent y. Be very, very careful with that rule, right? So this means that the logarithmic or log is really closely related to what? To exponent. That is why that's its condition there. So because logarithmic are really closely related to exponent, and we know these are just a reflection of exponential graph about the line y equals to x. So if I have something like log ax is equals to y, then I know that my x will be equals to a exponent y. I want you to really conceptualize this rule, because it's one of the most important rules, and that you really have to know. Okay, so let's just look at it on this example that I just put in this image below, and take a look at this one. So if we have log, you can see we have log 2 16 equals to 4, right? So we can say our 16 from part of our x will be equals to 2 exponent 4, and this is correct, because if you say 2 exponent 4, it will still give you what? 16. So you can see that condition, it's really correct. So if I have something like log sorry about this line, if I have something like log base 5 1 over 125 is equals to minus 3, then I can see that we can say 1 over 125 will be equals to 5 exponent 3 exponent minus 3, and you know that 5 exponent minus 3 will be 1 over 125, which will still be the same. So really know that. Okay, what about this one now? So this one is quite challenging, because now we don't know the base, right? We don't know the base. So what you learned, I think, when you are doing algebra is that, for example, if I have something like this and something like this, we know that these two are the same, right? This one is the same as this one. We know that there is 2 there, although they didn't put 2, but we know that that is a square root, so there must be 2. So if you punch your calculator like this and you punch your calculator like this, you still get the same answer, because there is 2 there. Also the same with logs. If they just give you log x, right, so it will be the same as log, but with logs there is 10 on the base. There's always 10 on the base, unless they just give you another number, right? So this is the same as log base 10x, right? And you can see that in your calculator there is somewhere on your far right hand side, just under that button for switching on your Casio calculator, there's a log button there where you can just press it, and you'll see it will show you base. You can put your 10 and you can put any number there to just get the answer of that. So just know that if they just give you like this, there is always a base of 10, even though they don't tell you, right? Just like in square roots, they can just put a square root without putting 2 there, but you know in your mind there's always 2, right? So same with logs, there's always 10 there. So if for example, this last example here, as you can see, it says log 100 is equals to 2, right? So we can know that here there is always what? There is always 10, even though they didn't put it. So we can see that 100 is equals to 10 exponent 2, 10 exponent 2. So you can see that really logarithmic are really closely related to exponents. So note when the base is 10, you don't write it down, right? So most of the time they don't write it down, they just give you like that. Okay, so let's also look at some special logarithmic values. Very, very important that you know. We have log base a1 equals to 0, right? Log base a1 is equals to 0. Why is it equals to 0? Because we can see that 1 is equals to what? A exponent 0. 1 is equals to a exponent 0. So 1 is equals to 1. So they're the same. So that condition really there, it's of paramount importance and very, very useful. So if I have log a equals to 1, then we know that our a is equals to what? A exponent 1. So just like that. So that's it. So let's now take a look at some logarithmic laws. Okay, so note that you will not be examined on manipulations involving the logarithmic laws, but it's very useful for understanding logs better. And also, this is not only useful in this topic of function. When we start to do finance, maybe we want to determine the number of years, you need to know some log rules in order to solve n there as an exponent. So you can see they are not only useful in function, but they are really also useful in understanding logs better and how to use logs to solve some problems in a different mathematics topic, such as finance. Also in your algebra, they might like to put them. Also in number patterns, if you want to calculate n, and maybe it's a geometric sequence and all that, and you want to solve that n on the exponent, you can use log rules. So they are very, very important. Okay, so you just only have four of them, although we have plenty of them, but for your grade 12, just need to know these 4. And the first one, it says log base CAB, a times b, right? So log base C a times b is the same as log CA plus log CB. So obviously if you are multiplying there, then it will be like it's closely related to addition. So if you are multiplying, it's closely related to addition. For example, if I have log base 6 plus, log base 6 2 and plus log base 6 18, so it's closely related to, because we are adding, we are just gonna multiply those things. So our base remains 6, then we just say 2 times 18, then it gives us 36, right? 36. So you can just punch that one on your calculator. You'll see your calculator will give you 2. But I also want to show you how you can just get the answer of this logarithmic without using a calculator. So this is the rule that you need to know. Very, very important. This one will help you to calculate the logs without using a calculator, just to know the answer. It's very, very important because there are some questions that will require you to know this understanding, to have this knowledge, right? So the rule just says if we have log a, then we know that here there is exponent of 1, right? So even though they didn't write it, then if this base here is the same as this value put up, that is put here, right? So then the answer of the whole logarithmic will just be the exponent there, 1. For example, if I have log 2 to exponent 4, right? Because this 2 of the base is the same as this 2, the answer of the whole log will just be equals to that exponent, which is 4. And you can prove that using your calculator. Just punch log base 2 to exponent 4 to just be 4. So that's the rule. It's very, very important for you to know. Okay, so you can see now, if I have log base 6, 36, we can see that 36 can also be written as log 6 into 36 can be written as 6 squared, right? So because this 6 and this 6, they are the same there, the 6 of the base and this 6 here, then the answer for the whole log will just be equal to the exponent there, which is 2. Okay, very important. But mostly important, I just want you to know this rule. If we are multiplying two values there inside, then it's the same as we can separate it and write it as if we are just adding them like that. So that's the first log rule or log law. Okay, let's move to the second one. Let me just delete this one a bit. Let's move to the second one. When we are dividing, you know that division is closely related to subtraction. So that's the rule. If we have log base c a over b is the same as log base c a minus log base c b. For example, if I have log base 6 12 minus log base 6 2, because I'm minusing is the same as, like, I can divide those values there, right? So it will be the same as what? There it will be the same as log base 6 into 12 over 2. You can see it gave them what? 6. 12 over 2 is 6. Because 6 and 6 are the same, the answer for the whole thing will be equal to the exponent there, which is 1. Or you can simply use your calculator there. Okay, so that's rule number 2. Rule number 3, it says log base c a exponent p. Okay, let me just write it clearly. Log base c a exponent p. So if you apply a log on an expression that has an exponent, so what basically happens is that log can manage to take that exponent on the other side. So the rules state that you can actually pull the exponent down and you'll be left with p log c a, right? So that's the rule. For example, if maybe for example, sometimes you want to solve for x, you have 2 exponent x equals to 5. You know that you can't raise 5 to the base of 2, right? It's really impossible. So you can use this log rule number 3 just to pull that x down so that you can be able to solve for x. Let me just show you how you can do that quickly. So if you have 2 exponent x equals to 5, then you know that if I apply log, you'll apply log both sides, right? So that you may not have broken any math rule. After applying log this side, anything on the exponent will go down according to this rule, right? So you'll have something like x log 2 is equals to what? Log 5. Now it's simple to solve x. You just divide by log 2, divide by log 2. Wow. You can calculate the value of x like that. Okay, so you can see that rule is very, very useful, and it's the one that is most useful also in finance. And I'll just show you there when we start to do finance. This rule number 3, very, very important. Just know if you apply a log on something that has an exponent, that thing on the exponent can be pulled down to be on the same straight line as that expression. Then you can just basically solve for the rest of the things there. So for example, look at this. We have log base 381. I can write 81 as 3 exponent 4, right? So you can see 3 exponent 4. So I can pull this 4 down here according to this rule number 3, right? Because I have a log there. So it will be 4, as you can see here, 4 log 3 3. But you know that log 3 because 3 and 3 are the same, it will be equals to 1. So it will be 4 times 1 to still remain what? 4. So you can prove that using your calculator. Very, very important log rule. Let me just highlight it with a star so that you may You may mark that down. Very important. 4. Let's come to rule number 4. It says log base BA is equals to log CA, log base CA, and log base CB. So what's happening here? So it's just that the way they wrote this, it's not really nice. Let me just show you using this one. Let me say log 2 into 3. So if I have log 2 into 3, this is called the change base log rule, right? It's sort of like change of base log rule. So what actually happens is that this can be written as log 3, this 3 that you have, over what? Over log 2, right? So but you know the base have changed from 2. We know if we just write log 3 over log 2, but we know that there is what? There is 10. Or you can put any base you like. Someone can just say log 3 over log 2, or maybe just use a base of 4. Any base you want to use. So it's change of base rule. Hence also here they just say log A over log B. This be the log B. It's just that they use capital letter and that was small letter, so it's quite confusing. So this should be a small letter also, because this was a small letter. So also very important when we try to solve the inverse of exponential function, when we try to calculate its equation, rule number 4 is going to be very useful, right? So let's just take a look at some examples here. If I have log 4 8, right, I can write it as what? I have log base 4 8. It can be written as what? As log 8 over log 4. I changed the base already because now the base has become 10. Although even though we don't write it, just know the base is 10, like that, right? So then that can be simplified and you can actually get the answer and all that. So using your calculator, definitely gonna get the answer. So I just want you to know these log rules, very important. Number 3, don't forget, it's gonna be useful in patterns. This number 3 is useful in patterns when you want to calculate the number of terms. If you are given a geometric series or a geometric sequence, it's also useful in finance. I'm just gonna show you when we start the series of our finance. Also very useful in algebra when you want to solve for x. And I just show you, if I have 2 exponent x equals to 5, I can apply log both sides and I pull that x down after applying that rule. So then I divide both sides by log 2, divide by log 2, then I can be able to solve for this x. So you can see it's also very important also in algebra. Rule 3, rule 4, it will be very important as we proceed with this lesson, and you're going to see. Okay, let's now focus on exponential functions and their inverses. Very important part of this section. How can we calculate the inverse of an exponential function? So in topic 2, you learned that to find the inverse of a function, you need to swap x and y. And you need to rewrite y in terms of x. So the same applies when you want to get the inverse of an exponential function. Don't forget, I introduced you to logarithmic rules. So it's going to be very simple to get the inverse of an exponential function. So there are 2 ways that we're gonna do this, right? There's a way in which you can memorize, which I don't really prefer, that if you have this exponential function, then its inverse, it's definitely gonna look like this, and it's just shown in this picture here. So for example, if we have y equals to a exponent x, then if we need to find its inverse like that, we're gonna swap x and y. Then when you calculate its inverse, you're gonna get it as y equals to log So now your base, it goes down to the base there, log ax down there. So that it is its inverse. So you can see it's a logarithmic function, which is the inverse of an exponential function. So if you have, for example, y is equals to 1 over a exponent x, then when you calculate its inverse, very, very simple also, y equals to its base still remain 1 over a and x goes there. So that's its inverse. But I just want to show you this using some log rules rather than memorizing. But in the exam, because you'll just get this having 3 marks or 2 marks, you don't really need to show them those log rules, right? So the more you practice how to calculate the inverse of exponential function, the more you'll be able to conceptualize it in your mind, and you don't need to use the rule. You just know, or we can say you just memorized how to do this. Okay, but I'm just gonna show you the rules, using the rules for your understanding. But you on the exam, you don't need to really show them those rules. What you just need, the more you practice, you realize, okay, I can just do this without the rules, because it's easier to memorize like that. So you are given f of x equals to 2 exponent x, and they say write the inverse in the form f exponent minus 1 x equals to something. So they need the inverse, right? So what's the first step of getting the inverse? Remember, in part 2 of our section, I introduced you to inverse of a function and steps on how to find the inverse. The step number 1 was that we replace f of x by y. So where there is f of x, I'm going to put y. Then step number 2, we then swap x and y. So where there is y, we put x. Where there is x, we put y, right? Step number 3, we have to solve for y. We have to solve for y. But look at your y now, it's on the exponent. And I told you that rule number 3 is very, very useful in solving exponential functions, right? I mean, in solving exponential equations. So in order to solve this y, I'm going to use a rule that will ensure that this y can be on the same linear position with all this expression. So in order to do so, I know that I have to apply log, right? Immediately apply log both sides, then it's going to work. So if I apply log like that, I apply it on my left hand side and also on my right hand side. In maths, what you do on the left hand side, you must do it on the right hand side. So after applying log here, the rule says then this y can go now and be in the same position as those things. So we'll have log x is equals to y log 2. Very, very gonna be easy to solve for y. We just divide by log 2, divide by log, sorry about this, log 2. Then this log 2 and log 2 cancels. Then you are left with y is equals to log x over log 2. Okay, think of rule number 4 now, right? Rule number 4, it says if I have log a over log b, it will be the same as log b a. So that's the rule. If I have log a over log b, it will be the same as log base b a. So even here, because I have log x over log 2, it will be the same as log base 2x. So this is my inverse. So I can write it in that form they need it, is equals to log base 2x. That's the final answer. Okay, so you can say I only use 2 rules. The first rule that I use is the one that you apply log, and once you apply log, everything that is on the exponent goes down to the same linear position as the rest of the equation. Then you can solve for y like that. Then you'll realize your answer for the inverse is this one. Inverse of f of x will be equals to log base 2x. But really in the exam here, I'm just showing you just for your understanding to apply log rules, because it's very, very important on some chapters like finance and all that. So just for your understanding, I'm just showing you these log rules. At schools, they won't really show you, but it's very, very important that you know them, so that you may not only memorize and just know how to get the inverse, but also have an understanding of where does this comes from. Okay, so you can see, because most times most people, if they just see y equals to 2 exponent x, they know. Okay, it's okay. As I was saying, that if anyone just see an equation y equals to 2 exponent x, they just know that, okay, its inverse is simple, because this is an exponential function, then its inverse I just put log, then on the base I put 2, then like that, then that's the answer, you see. So but also you can follow the understanding part, so that you conceptualize this. Then the more you practice, more questions that requires you to calculate the inverse of an exponential function, then you'll just be able to do that very quickly. Okay, here just want you to show you this this shape of logarithmic functions for these two different kind of exponential equation. So the first exponential equation is y equals to a exponent x, and we can see that from the equation here, we can see that here our a was what? Here our a was greater than 1, right? Because it's an increasing exponential function. If you raise up your right hand, you realize, okay, the shape that your right hand is forming is the shape for an increasing exponential function. So once we reflect that one about the line y equals to x, we're gonna get y equals to log base ax, and that's gonna be its shape. You can see its shape. So in order to sketch it, if they require you to sketch the inverse, you just know the points for the original function, then you just swap them, right? Once you swap them, it will give you that kind of shape like that, and that's the logarithmic function for that. So let's go to the second one. For a decreasing function, for a decreasing exponential function, y equals to 1 over a exponent x, then we know its shape is going to be like this. If you raise up your left hand, right? If you raise up your left hand, the shape that your left hand will form is for a decreasing exponential function, where your a is between 0 and 1, right? Once you calculate its inverse, you'll realize it will be log base 1 over a x, right? So once you sketch it, once you swap the points, that will be the graph. So but you can just now know how the shape can be for this logarithmic function, when it's of an increasing function and when it's of a decreasing exponential function. Okay, so far I've been showing you how to calculate the inverse of an exponential function, and I say its inverse, it's a logarithmic function. So now in this example, I just want to show you how you can also calculate the inverse of a logarithmic function, right? So the inverse of an exponential function is a logarithmic function. Same goes with the inverse for a logarithmic function. It's a exponential function. So obviously the inverse of a logarithmic function will just basically be an exponential function. Number one, let's go. You have y equals to log base 3x. If they say calculate the inverse like this question, we are going to swap x and y. Where there is y, I put x. Where there is x, I put y. This step has a mark. Very, very important. Whether you fail to calculate the final answer for the inverse, make sure that at least you show you have swapped x and y. It has a mark, because they realize you understand the content and what has to be done, right? So now we go to the solving part, right? In order to solve now, I want to solve for y, right? So remember that other rule that we start with, that y, this value here, will be equals to 3 exponent x. So that value there. So we say 3 exponent x. So this is our inverse. and they say we must write it in this form, so I'll just leave it in that form there. So that's it, right? Okay, let's go to number 2. You are given y equals to log base 1 over 4 x. They say find the inverse in the form of y equals to something. First step, we swap x and y because this has already been written in the form of y equals to, so we don't need to replace f of x by y. It has already been reflected, replaced. It has already been replaced by y. So I'm going to swap x and y. Where there is y, I put x. Where there is x, we put what? We put y. This step has a mark. Don't forget. Every time when they say calculate the inverse, don't forget to swap. It has a mark, right? Then I can solve for y. How do I solve for y? Don't forget that rule says this 1 over 4, then exponent x. So that's the answer. Just get your 3 marks or 2 marks for doing that. Okay, let's look at some of the extended examples that I just put here for exponential and logarithmic function. I'll just do maybe one of the question, then the rest of them you can just try them as your fun activity exercise. Okay, so it says for which values of x is sorry about this. Okay, so it says for which values of x is the first one, it says the log of base 2x less or equals to 3. How do I solve this now, right? So to solve this, you need to get what I call critical values, right? So critical values that are most important values for these things. Okay, so in order to get them, you have to solve for x really. So assume here there's an equal sign, and if there's an equal sign, how would you solve for x? Let me do it like this. If there's an equal sign, how would you solve for x? Just say, don't forget that rule, x equals to 2 exponent 3. X equals to 2 exponent 3. This will be equals to what? It will be equal to 8. So that's your critical value, right? So now to get the final answer for which your log base 2x will be less or equals to 0, it's when x is less or equals to 8. It's when x is less or equals to 8. But don't forget the condition there. Remember, x must also be greater than 0. Always don't forget to put that condition to say x must be greater than 0. It must not be equal to 0. So we are saying x must be less or equals to 8, but also x must be greater than 0. Why? It's because if you sketch your logarithmic function, mostly it's either you get it in this way, or if this is the x-axis and y-axis, and sometimes the other one it just be in this way, right? So you can see they don't touch 0. Your x will never be equal to 0 there, right? So it's always going that side for the value of x. Hence we always need to say x must be greater than 0. Don't forget to put this restriction, and this was your critical value, x was less or equal to 8. So that's how you do it. So just go and try to do 2, 3 and 4 as your fun activity exercise, and just post your answers on the chats. Okay, not on the chats, I mean on the comment section. Okay, great stuff. This marks the end of our session. We're doing part 3, where we're focusing on exponential functions and logarithmic functions. Thank you very much for joining. Thank you very much for watching. This marks the end of our session for function. The other sessions, I will just post them later, not now. This was just grade 12 functions, that this new added knowledge in your grade 12 function, and it's all covered in the 3 sessions that we had: part 1, part 2, and this last one, part 3. So thank you very much for watching. Thank you very much for joining, and enjoy the rest of your day. Okay, goodbye.